Hey everyone. Hello guys. Good evening. Welcome. I am good. Thank you. Yes. Thank you. Thank you so much. How are you all? Yes, सब लोग. All good at your end, everybody. Awesome. Raining in Pune. That's good. It's not raining in Mumbai today. Namaskar. Good evening. Okay, got it. Shyam Sundar. Got the weather update from you. Okay. No, I did not have dinner. We'll have it after the class. Did you wish your teacher? Who is my teacher? What's for dinner? You know that khichdi as always, nahi? uh, uh. So, how is everyone? गिफ्ट तो तुम लोग ऐसे पूछ रहे हो जैसे सबने मेरे लिए गिफ्ट भेजे हैं. हाँ, how many of you sent me gifts? You don't have to have my address. You can send it on Vedantu's address. वहां से मेरे पास आ जाएगा. Deleted नहीं होता, belated होता है बच्चे. Nobody will steal it. Don't worry. Sir, upcoming Children's Day gift. Exactly. वो भी भेज सकते हो तुम मुझे. Okay. So everyone, hope everybody is ready for session number 2. वेदांतु ने क्या दिया वो मैं तुम्हें दिखाता हूँ बाद में. ठीक है. तो फिलहाल let's start the session. Everyone, quickly, everybody say hi to your class teachers. Quickly, say hi to your class teachers. We have Rishabh sir, Gautam sir, and Anshul sir as your class teachers. Okay. Did your hair grow again? नहीं ना यार, देखो यहाँ खेती नहीं है, यहाँ खेती जा रही है. So there is no growth at all. Okay, so I can see a few students are new in the class. Those who are new, for them, this is our session number 2 of rotation motion. So definitely you need to watch the previous session. And if you are not in sync with the class itself, then you'll have to probably watch the previous the classes that you have missed. You'll have to watch them as well. Okay. ठीक है, चलो मुझे बाद में सजेशंस दे देना मेरे हेयर ग्रोथ के लिए. फिलहाल रोटेशन मोशन पे फोकस करते हैं. एवरीवन, व्हाट से, शैल वी स्टार्ट? वी हैव अ सेशन वेयर यू विल सी अ फ्यू इंटीग्रेशंस टुडे. सबको बिस्किट थियरी याद है? सबको बिस्किट थियरी याद है? एवरीबॉडी रिमेंबर्स द बिस्किट थियरी? So we will be having session number 2 of usage of biscuit theory today. Absolutely. So the idea has to be clear. You will be able to understand the biscuit theory application once again. Okay. So everyone, write +1 if you are ready for the session. Great. Okay. So everyone, switching off the chat. We will start the session. Okay. Chat is off now. We will be first revising what we studied last time. Okay, quickly, and then we'll start today's session. Today's session is really important because if you people remember what we did last time, we did a basic introductory part of rotational motion. We understood the underlying difference between rotation motion and circular motion. I will just give you one example which will give you again the recap of what is the difference between rotation and circular motion. When we speak about motion of Earth about its own axis, okay, so the rotation of Earth about its own axis is what we call as a rotational motion. Okay, where the body is a rigid body and different point particles are moving in a different circle of their own radius. But when we consider Earth ka motion about sun, so the distance from the sun to Earth is actually much bigger in comparison to the size of the Earth. So we can consider Earth to be a point mass when it is revolving around sun, and in that case, the motion will be called circular motion. Okay, so basically circular motion is the property of point mass, or it is defined for point mass. While if the body becomes relatively bigger, then the motion becomes rotational also. Okay, or in a nutshell, rotation motion is basically collection of multiple bodies circular motion. Many bodies performing circular motion collectively, system of particles moving in circular motion of different radii will be known as the rotational motion. One very important thing that we understood that whenever a body performs, the rotational motion, okay, the angular displacement, angular velocity, and angular acceleration of the entire body and all the particles remains the same. Okay. Then we talked about not just angular velocity omega, we spoke about alpha also, we spoke about theta also, we spoke about different equations. This is something which came as a recap from circular motion, and that is when we went to the most important part of the topic or the chapter called as moment of inertia, defined as capital I. It is a tensor quantity. That's what I also explained there. More importantly, the moment of inertia for a point mass was defined as mass value multiplied with the distance from axis of rotation ka square. So we will not call it radius, we will call it distance from axis of rotation. Obviously, a point mass when it moves along an axis of rotation, its motion is circular motion. But we are trying to deliberately get into the habit of saying it not as radius but distance from axis of rotation. Okay. If you have multiple particles which are forming such motion, then the moment of inertia for multiple particles will be m1 r1 square plus m2 r2 square. Like that, as many particles which are there, we'll simply keep on adding all the moment of inertia for multiple particles. This is what we did last time. Okay. So now today we'll be taking our discussion into the domain where particles are not having distinguished visibility. They will be there, but they are actually forming a rigid body. That means what? Like if we speak about my bottle, this bottle is actually made up of multiple small particles, and if this bottle rotates like this, if this bottle starts to rotate like this or like this, all the particles are moving in their own circles, but you can't say where exactly one particle is and the other particle is. There is no distinguishable boundary. So this is a continuous body, this is a rigid body. Okay. Actually, there is no body in this universe which is rigid. I hope you will remember, rigid body is the one whose shape and size will never change. So for our understanding, we will say a solid body is a rigid body in our chapter. Okay. So guys, what is our discussion now? We want to basically find out the moment of inertia of a body, which is a continuous body. So how the discussion happens? This will be related to the biscuit theory. What biscuit theory said? We will have different shapes of object, like a rod, a ring, a disc, a sphere, different objects, and we are going to split them into small pieces of definitely the same mass. Those same mass particles will be the small biscuits, which are going to have the value as dm. Okay. One randomly chosen dm mass is at a distance r from the axis of rotation. So if we only focus on our small elemental mass dm, then when the body rotates, this particle moves in a circular path. If I want to write the moment of inertia of this particle, that moment of inertia will be only di, which is basically one of the particles' moment of inertia, and that will be written as its mass into distance from axis of rotation, the square of that value. Or you can say the radius square, as I said earlier also. We will try to get into the habit of not saying it radius, but we'll just call it r, which is the distance from axis of rotation. So we basically want to write this dm mass in terms of the mass of the object, in terms of its physical dimensions, maybe L or R, Okay, depending upon what kind of body it is, and we will try to write down the moment of inertia by integrating of the entire body. That's what we are going to do. We're going to integrate this thing. So when we integrate, we're going to get the moment of inertia of the entire body as integration of dm into r square or r square into dm. That's going to be the basic idea. And what better than doing some derivations to understand how it works? Okay, so I'm going to show you guys a series of derivations now. So all eyes on the screen. Keep your ears on. Keep your eyes on the screen. Try to refrain from asking random doubts to your class teachers at the moment. As I'll be done with all the derivations, I'm telling you, many of your doubts will naturally be clarified as always. If not, then you keep them noted. You know I will take those doubts later on after I switch on the chat once a significant amount of derivations are done. Okay, so chalo guys, what are we going to do? We are going to talk about the moment of inertia of a rod. We are going to speak about moment of inertia of a ring. We are going to speak about moment of inertia of a disc, hollow sphere, and solid sphere. These are the most important objects. One by one they'll come. And if you people remember moment of inertia as a tensor quantity, if you have different axes of rotation, the moment of inertia is going to be different. So right now the derivations that we are going to do are going to be about the axis which is the most standard axis for that object, most probably passing through the axis of rotation, passing through the center of mass itself. Okay, guys, so that's what we are going to do now. Okay, so everyone, the first object is this. This is basically a rod whose mass is m, whose length is l, and the axis of rotation is passing through its center, and this thing is rotating. How it is rotating? If just a second, I will take a, yeah, we have the colorful pens. If this is that object, the one that I'm talking about in the diagram, the one that you see in the diagram, is a uniform rod. Uniform rod means its density is uniform, and this is going to rotate like this. Means if I place it on a surface, it's going to rotate like this. So axis is passing through the center. Axis is passing through the center and perpendicular to it. So this is how the rotation is happening. Right. So this is a uniform rod, obviously. So we want to find out its moment of inertia. What is AOR? I hope you people remember. I told you last time. AOR is axis of rotation. I'm going to write only AOR. We will never write entire axis of rotation. Okay. So this is what is AOR. Okay. So now we want to find out the moment of inertia. So if you people remember, we did the red rod ka center of mass ka location we found by considering it to be like a biscuit packet. Here also we are going to do the same. So this is basically our origin. This is origin. And if this is origin, then definitely the rightmost end, this one, is at a distance L by 2 or plus L by 2. And the leftmost end is at a distance minus L by 2 because origin is at the center. Okay, so this is how this is done. And as I said multiple times, the derivations that I do are to be not only just seen, you have to understand and remember the approach also. So that if ever your school examinations will ask you to do this, you will be able to replicate this process. Okay, definitely JEE will never ask you to do the derivations. So everybody, what we are going to do, we are going to consider a small particle here whose distance from the axis of rotation is say x, its size is dx, its mass is dm. Okay, its mass is dm. As this thing has uniform linear mass density, this object has uniform linear mass density. I hope you people remember what is linear mass density. It is mass per unit length. So what we are going to do, we are going to say that for this object, when we try to write lambda, the lambda is written as the entire mass of the rod divided by the length of the rod. Okay, the beauty of uniform mass density is that it is going to be the same value if we write it for the small biscuit, that is dm mass. So what is the value of mass? That is dm. What is its length? Dx. That's how we write it. Mass per unit length for the entire rod, mass per unit length for the small biscuit also. It's going to be the same value. I hope my investment there in the chapter of center of mass must be paying the dividends now. You must be able to understand this very straightforwardly that this is how things work whenever we speak about discrete theory. Okay, what is my objective here? My objective is to extract the value of dm in terms of capital M and L. Capital M and L are constant. Okay, so this is how dm comes out to be. Now I want to find out the moment of inertia I, and moment of inertia for the entire object will be integration of the moment of inertia of the small mass. Small mass ka value dm, its moment of inertia is dm into x square. How is that so? It's like a point mass. It's a very thin rod, okay? It's a very thin rod. In the diagram, it may look like a proper scale or a very thick rod. It is actually a very thin rod that we are talking about, like a wire. A wire is being rotated. It is that thin that we are talking about. So basically, that small element is like a point mass, and point mass is moving in a circle. So when a point mass moves in a circle, the moment of inertia you write it as m into r square. But now the mass is dm of that small element. That's why what you're writing its moment of inertia as you're writing it as dm into x square. Its radius is x right now. And as I said, we will not call it radius. We will call it distance from axis of rotation. Okay, people. Now, as I said, dm ko pata lagana, the finding value of dm was basically a very important point to do. So now we are going to put this dm here. We will write it as m by l into dx into x square. So constants will be taken out of integration, and integration will happen for x square dx. Integration limit minus L by 2, the leftmost end to the rightmost end. Okay, guys? No, you will not take this point as O because of the axis of rotation location. Wherever the axis of rotation will pass through, usually we consider that as origin. Okay, people? So you know now that in biscuit theory, finding the equation or making the equation to integrate is the real task rather than integration. Now integrating x square is a piece of cake. It's basically bachpan ka sawal for us, right? So m by L integration of x square is going to be x cube by 3, x to the power n plus 1 upon n plus 1, going from minus L by 2 to L by 2. Okay, guys? So m by 3L, 3 came out. And instead of x cube, we'll be putting the limits. So when I put the limit L by 2, the cube comes out to be L cube by 8, and this comes out to be plus L cube by 8. Why? Because minus L by 2, the cube of that is also minus L cube by 8, and minus minus became plus. You can try that yourself. This is what you'll be getting, and it is m by 3L into L cube by 8. Sorry, L cube by 4, because this is L cube by 8 plus L cube by 8. Adding it will be 2 L cube by 8 or L cube by 4. Simplifying it overall, finally, everybody, the moment of inertia comes out to be very important result, ml square by 12. That's the result that we get. Is the derivation important? Actually, no. But what is important is definitely the final result. Final result is something that I want you people to remember. And more importantly, remember where the axis of rotation is passing by. It is passing through the center of mass. It is passing through the center of the rod. That is very important. Many students make mistake with the rod. Please remember the axis of rotation is passing from the center of mass, which is the center of the axis of center of the rod also. It is only valid. The result that you see ml square by 12 is only valid when the rod has uniform linear mass density. Unless the question says that linear mass density is not constant, you will always write it as ml square by 12 when the axis of rotation is passing through the center of mass. Okay, people? Take a note of the result. Take a note of the result. ml square by 12, the axis of rotation passing through the center. That's the moment of inertia. This is the laziness of the body. What is moment of inertia? It is the laziness of the body. And the laziness result for rod is going to be ml square by 12. Okay, good enough. Awesome. Sure, guys. Taking you to the next object. Okay, next object is going to be the ring. So we have a ring whose axis of rotation is passing through the geometric center perpendicular to the plane. That means what? The ring is going to rotate like this. So this is the axis of rotation. You see this? This is the ring. Can't make it vertical. It will be very difficult for me to show it. This is our ring. It's going to rotate like this. Very difficult for me to show. Only focus on the golden part. So this is how it is going to rotate. Like that. Okay. So this is how it's going to rotate. and the axis of rotation is visible in the diagram. The mass of the ring is m, the radius is capital R. We need to find out the moment of inertia of this thing. The point is, this time the biscuit packet has a shape of ring, and all the biscuits are of mass dm. And if we speak about its thickness, for that I need to take you back a little back when we did the derivation. Also, I showed you this. I hope some of you will remember it already. Okay, so this is our ring, and this is our center. And say I talk about the small element that we have drawn here. This is our small element. Not letting it draw only. Okay, so basically, this small portion that you see, all of you, this is basically subtending a very small angle d theta. This is radius r, and this distance is going to be r d theta. I've said this a number of times. Arc length divided by radius is the angle. So arc length, this arc length comes out to be r d theta. Okay, everyone. So if we say that it has mass dm, okay, then we will say it has, again, this, all the objects that we are speaking about, they all have uniform density. Now this is a rod which has been converted into a ring. You know that the rod is converted into the ring. So again, uniform linear mass density. Okay, people. Spelling kuch gadbad hai. Density. Yeah. So again, uniform linear mass density. So what I'm going to do, I'm going to say that the lambda value for the rod, sorry, ring, its mass is m, its length is 2 pi capital R, while this small element has mass dm, and its length is equal to r d theta. That's how we write it. And we have done the same thing. If you will go back today and recap the notes of center of mass of the ring, you will find the same thing is being done. There we have done the center of mass for a semicircular ring, because for the entire ring, the center of mass was at the center. That's why r gets cancelled. The value of dm comes out to be m into d theta divided by 2 pi. So we got the value of dm. Now you see that if this is my small elemental mass, if this is my small elemental mass dm, then this dm element, when the ring rotates in a circle of radius capital R. So the moment of inertia di will be dm into r square. All the particles are at the same distance. All the biscuits that we will be choosing, you will see that all of them are at the same distance, unlike the rod case. In the case of rod, different elements which I will choose, they are at different distances from the axis of rotation. But the beauty of the geometry of a ring is that all the elements are at the same distance from the axis of rotation, that is capital R. So if I want to find out the moment of inertia, okay, I will be doing the integration of dm into r square, and we will not even require this lengthy thing that I've written. Why? Because I'm going to do the integration of dm directly. If I add the mass of all these small elements, all these dm elements, if I keep on adding their mass, what am I going to get? I'm going to get the mass of the entire ring. So that is why this is 0 to capital N. The minimum mass value could be 0. If you want, you can put this also, by the way, no problem with that. But then the integration limit will be for theta, and the integration limit goes from 0 to 2 pi. Okay, I don't want to complicate things. If you people want to understand that also, wait till the end of the class. I will explain that also. That if I, instead of directly integrating dm, if I would place this as dm and then integrate from 0 to 2 pi, the result will be unchanged. I just don't want to make it lengthy. That's why I'm directly doing it. It is perfectly acceptable also. Okay, so r square integration of dm will be small m, putting from 0 to capital M. Look at the result. Beauty of the result, it is same as that of point mass. This is the result that we are getting. The moment of inertia of a ring, when the axis, again, which axis you are talking about is very important. The axis is passing through the center and perpendicular to the plane of the ring. That is what is very important. Now here only, people, the result is very simple. It is the result of the point mass only. When a point mass moves around a axis, you remember the moment of inertia came out to be mr square only. So basically, what is happening here? You have to visualize this part with me. If I take this point mass, I keep on elongating it like it is it's like a elastic. Say if I'm able to elongate it like the way glass is made. Glass is something which can be stretched. So imagine this point mass can be elongated and given a shape of a ring. The entire mass is still at the same distance r. A point mass is also at a distance r, and if you convert it in the form of a ring, still the entire mass is at the same distance r. That is why the moment of inertia is coming out to be same. If you people were paying attention to class number 1, session number 1 of rotation motion, moment of inertia depends upon mass. It depends upon the distribution of mass also. It depends upon the shape, obviously, but it also depends upon the distribution of mass. This is the perfect example to understand it depends on distribution of mass rather than anything else. If you have the same mass which is at a distance r, however you arrange it, as long as your mass has same distribution with respect to axis of rotation, the moment of inertia will not change. So beautiful example, point mass and a ring, if they have the same value of mass, same radius in which they are moving, distance from axis of rotation rather, then the value of moment of inertia will come out to be same for point mass and the ring also. Remember, it's a very beautiful point to understand if you're keeping your understanding clear. If you're also trying to not just remember the values, remember the expression, if you're trying to actually get the feel of moment of inertia, this is a very beautiful point to actually understand. And very rarely I will be able to give you an explanation like this where, you know, the distribution of mass is explained and understood so well. Today we'll do a quiz question also. That is where also you will see the beauty of this point. That it depends upon distribution of mass. It does not depend upon anything else. By the way, guys, if I will take this ring and I will close it like a book, means what? If I will say imaginarily about this line, if I fold the ring and I make it a semicircular ring, and I still rotate it about the same axis of rotation, that means what? This is my semicircular ring. This is my axis of rotation, and this is how things are rotating. So still the moment of inertia will come out to be mr square. Why? Because still the entire mass is at the same distance. If you will make it 1/4 of the ring or any portion of the ring for that matter, as long as you are having entire mass at the same distance, the axis of rotation being the same, the moment of inertia will come out to be the same value. Point very important that you need to keep in mind. Okay, guys? Cool? Good. So this is your ring. Moment of inertia, mr square, about an axis passing through center, perpendicular to the plane. Perpendicular to the plane is very important. Okay? Good enough. Now, guys, obviously the next object is going to be a disk. And the disk obviously will have a uniform surface mass density because it's a 2D object. So it has uniform surface mass density. आज थोड़ा theory है बच्चों. Okay, we have theory today to cover, but don't worry, we will have collection of problems also to solve. Let me go through these moment of inertia derivation. After that, you will see we have so many questions coming up for all of us to solve. Okay, so it has uniform surface mass density. That means sigma. That is mass upon area. That is constant. That's what it means. Okay, so now if you people remember Kachua Chhap Agarbatti or Mortine coil, this is actually made up of multiple rings starting from the center till the periphery. That means what? If I consider a ring here, then here, then here, I will keep on putting more and more and more and more rings one by one, the entire disk is formed. So basically, the packet of biscuit is like a disk. The biscuits are ring, and that too of different radii. So here, what you see, everyone, I am drawing one of the randomly chosen rings. I'm going to draw that. Already it is drawn. I'm going to make it a little bigger for you to see. Okay. So this is our biscuit. This is our biscuit, whose radius is small r. Okay, and the radius of our disk, let me write it as capital R. I don't want it to be small r. This is capital R. And here also I have to correct it. The radius of the ring is disk is capital R, and radius of the biscuit ring that I have chosen is small r. Okay, everyone. So now you see, if I write sigma, the surface mass density, which is mass of the disk divided by its area, that is pi r square. I gave you guys an explanation on this also. Those who do not remember this, I gave you an explanation. The area of the ring is written as its circumference. First of all, I'll write down its mass to be dm. This mass is dm. Its area, how will you write the area? You will say the circumference, which is 2 pi r, multiplied by the thickness, that is dr. Again, for those people who were there in my session of center of mass, they would be able to relate it straightforwardly. Those people who are first of all new in the class, as I know some of you guys are new in the class, maybe their first class this was. So I want you people to definitely go through the sessions of center of mass. Center of mass, only one session we have done, and in that session we have done derivation. I've taught you something called as my biscuit theory. You will be able to go through all these points. You will be able to understand how this comes, how 2 pi r dr is the area of a ring. All those explanations are there. Okay, so everybody, let's write down m from here, small m, dm actually. So pi gets cancelled, and now dm comes out to be 2 capital M r dr divided by capital R square. So this is basically the mass of my ring. And what is the moment of inertia of a ring? The moment of inertia of the ring is dm into r square. We just now found the moment of inertia of the ring. It is mass of the ring multiplied by its radius. So now the ring that you see, okay, this ring that you see, the biscuit. Just a minute. Okay, so ring the biscuit, its moment of inertia is dm into r square. You'll be putting this dm here, and then you'll be integrating. So moment of inertia is going to be integration of 2 m r dr divided by capital R square multiplied by small r square. So 2 capital M and capital R square come out, and what you're left with in the integration is r square into small r, that is r cube, into dr. What is the minimum size of the ring that I can form? The one which is at the center and has radius 0, and the one which I can form at the periphery, at the extreme of the disk, is basically capital R. Okay, guys. So 2 capital M by r square, the integration of small r cube will be r to the power 4 by 4, and we're going to put the limits from 0 to capital R. So 2m by 4 r square into r to the power 4 is what I'm going to get. 2 and 2 will be cancelled. Finally, the result that you get is half capital M into r square. This is the moment of inertia of a disk about an axis. Again, axis is very important. Which axis that I'm talking about is very important. So the moment of inertia is going to be about an axis that is passing through the center perpendicular to the plane of the disk. Okay, that means your disk is rotating like this. Either clockwise, anti-clockwise, does not matter. What matters is it is rotating about an axis passing through the center of the disk and perpendicular to the plane. Okay, so we've got this also. So far, the rod about the center 1 by 12 ml square, because for that you don't talk about r, you talk about the length of the object. For the ring passing through the center perpendicular to the plane, when the ring was rotated, moment of inertia was mr square, and for the disk about the same axis of rotation, it is half of mr square. The moment of inertia has reduced. Why? Because some of the mass has come closer to the axis of rotation. Earlier for the ring, the entire mass was only on the periphery, only on the circumference. The mass was there for the ring, but for a disk, mass has actually come inside in the circumference. So definitely mass has come closer. So the moment of inertia will decrease. More mass closer to the axis of rotation, less is the moment of inertia of the body. Okay. Hope you guys are able to understand this so far. Chat is on. I hope. I want to get the general feeling. Are you able to understand this so far, everyone? Feel area, that is what is very important. Obviously, final results are more important than the derivation. But if you understand the derivation, it is no harm. It is definitely going to increase your understanding towards things that you're learning today. Okay. Very few times you find me actually getting into much of theory, but at times it is required. That's why we do it. Okay. Very good. These are asked in school. That depends on your school, but most likely they do ask at times. Okay. Chale, again, other objects will speak about now. 3 more objects. We have already spoken about 3 objects. Now 3 more objects. Probably this is the lengthiest of all. Okay. This is going to be the lengthiest of all. This is the moment of inertia of a hollow sphere, hollow complete sphere. Okay. And the axis of rotation is passing through its diameter. Okay. Means the way the basketball player rotate the ball and they balance it on their fingers. Hollow basketball rotated on the fingers. That's basically your moment of inertia of a hollow sphere. Conditions or things which are known. Mass is m, radius is r, and it has uniform surface mass density. Surface mass density, mass per unit area is constant, is same. Okay, guys. So you see that the radius is already mentioned, is r. Now, in this, how we are going to do the derivation, I will come to that part. But before I come to that part, I have to tell you something which is going to be useful in the derivation, and that is basically a integration. What is that integration? It is the integration of sine cube x. Integration of sine cube x dx. Okay. Now I do not know whether you guys have come across the formula of sine 3x or not. Okay, even if you have not come across the formula of sine 3x, it is still doable. How? I'll show you that also. You people know the formula of sine 2 theta. Sine 2 theta is 2 sine theta cos theta. So if I have to derive the formula for sine 3x, I will say it is sine 2x plus x. That is sine 3x. And now I'm going to do what? No, I will require this formula also. This is sine a plus b right now. A plus b. So how will I write it? I will say it is sine a cos b plus cos a sine b. So when you simply put the expression of sine 2x and cos 2x and simplify it further only in terms of sine, then this is the expression that we get. Okay, guys. Are we all clear with the formula? Have you guys seen already this in mathematics, sine 3x? If not, then you don't have to worry about it also. If you have not seen, that's totally fine. You can as of now remember this expression. Sine 3x is 3 sine x minus 4 sine cube x. Okay? Okay? Please, not now, Ansh. You can ask your doubts after I'll tell you can ask the doubts. Not right now. Okay? Good enough? Okay, yes. It will be done in mathematics also. So I've given you the clue that how do we reach there. Okay? So more or less, if you have this expression sine 3x, which is 3 sine x minus 4 sine cube x, we want to extract the sine cube x from here. So sine cube x can be written as 3 sine x minus sine 3x divided by 4. That means we are just separating out this sine cube x from here. And the part that we want to solve, this is the main question. We will write sine cube x as 3 sine x minus sine 3x by 4, the integration of it. So 3 by 4 comes out, integration of sine x. 1 by 4 comes out, integration of sine 3x. Okay, guys? So integration of sine x is minus cos x. Integration of sine 3x is minus cos 3x by 3. Okay, this is x. Don't take it as pi. It's x only. Okay, so we get that. And when we write this after integrating and simplifying, we get minus 3 by 4 cos x, minus minus becomes plus, 3 into 4 becomes 12. This is the result that we get of integration of sine cube x dx. Actually, there will be a plus c also. I'm deliberately not writing it because it is a definite integration that we are doing eventually. So what are the limits for sine is what will help us eventually. So we are going to integrate this, say from 0 to pi. If we integrate it from 0 to pi, why? Don't forget that we are going to use this for in moment of inertia of hollow sphere. So I'll tell you how the angle is going to be 0 to pi for the integration. But as of now, you need your focus on what you do after the result of integration is found. You will be putting the limits from 0 to pi. Okay. So in the definite integration, I'm going to now put the limits minus 3 by 4 as it is. Cos pi minus cos 0 because I'm putting the limits. So cos of pi minus cos of 0, cos of 3 pi minus cos of 0. Cos of pi minus 1, cos of 0 is also minus 1. So minus 1 and minus 1 is minus 2. Minus minus becomes plus. I get 3 by 2. This thing becomes 3 by 2. Similarly, this is also minus 1 becomes minus 2. So I get minus 1 by 6. Simplifying it further gives me 4 by 3. Eventually, what I'm trying to tell you, the integration of sine cube x from 0 to pi comes out to be 4 by 3. As simple as that. Okay. If it would have been from 0 to 2 pi, the result will come out to be 0. But it is from 0 to pi. And what is important for me is this final result. This result is more important. 4 by 3 is the result of integration of sine cube x. Okay, guys. Now, let me tell you how do we do the integration of moment of inertia for a hollow sphere. So first, let me tell you how do you visualize this. I will visualize it as it is made up of multiple rings starting from North Pole to South Pole. I will have multiple rings placed from North Pole, increasing the size of the ring coming to the equator, then decreasing the size of the rings that I'm talking about. Okay, guys. That means the first ring that I will be forming is here, then here, then here, then here, like that. I'm increasing the size till equator, then I'm decreasing the size till equator. That's how the size of the ring is changing. Now, if you look at its angular position like this of any random ring, any randomly chosen ring, forget about what is written around it. Right now, just focus on the angular location of the ring. When I talk about the angular location of the ring as theta, the theta is actually made by the distance of this r vector. R vector is basically line joining the center of the sphere to the circumference of the ring. Okay, basically a cone kind of shape will be formed like this. Okay, so one of the sides of that cone is basically the radius of the sphere itself. Okay, so if you consider the ring to be here, then just imagine this r vector or r radius going vertical. Right now it is making some angle theta with the vertical. If the ring, black ring that you see is on the north pole, this length will become perpendicular. Theta value will become 0. Theta value will become 0. Now if I have to go on the other side of it, my hand will not go like that, but my hand will actually have to go 180 degree on the other side. That means what? This length will be measuring the angle of this radius. So that angle will come out to be pi, 180 degree. Guys, are you able to understand this? Right, plus one if it is clear. Getting it? You'll have to use a little bit of visualization here with me. Okay, if the topmost point, the ring that is formed, the angle is 0 degree. The bottommost point, this vector will have to take an angle of 180 degree. Yes, you can say that. Okay, perfect. Yes, Nitya. Were you there in the center of mass explanations? So imagine this entire sphere being cut into multiple rings. I'm going to cut it like this. Multiple rings will be cut. So you see that this is how many rings will be formed. Each ring with very small thickness. Okay, the topmost ring is the first ring. The bottommost ring is the last ring. Or you can say north to south pole. Okay. Now imagine a randomly chosen ring has this as the position denoter of it, which is basically the radius of the sphere. At different locations, if I locate them, all of them will be located by the same r vector, or rather same radius r, but making different angles with the equator. Do you understand this? So if I have my ring number 1, what will be the angle of this blue vector, the topmost point? 0 degree for sure. And if I have to bring that ring to the bottommost point, south pole, then the angle will be. This is how the vector will rotate. Correct? Angle will become 180 degree. So that is the limits for the angle theta that we are talking about. Okay. Now our job will be to write down the dm mass of this ring. Okay. Let's see how we are going to do that. Okay. So everyone, this is our ring, and as you know that all the rings have different angular locations, and not just that, their sizes are also different. By size we mean their own individual radius. Small r is also different. The topmost ring is 0 radius, the bottommost ring is also 0 radius. I cannot integrate from 0 to 0. My answer will come out to be 0. So my integration will be for theta from 0 to pi. This is actually to be remembered if you ever have to do the integration of a hollow sphere. Yes. If you ever have to do the integration of a hollow sphere, this is a standard procedure that I'm showing you people. Not just for sphere, the ring, the disc, the rod, whatever you have seen so far. The quantities may be different. Center of mass, maybe you are finding the center of mass. Here we are finding the moment of inertia, but the approach is standard. This is how the biscuit theory works. Okay, guys. So for the black ring that you see, say the surface mass density for the entire sphere has mass capital M, and the area of the sphere is 4 pi capital R square. Now you see, guys, the ring which you see here has a radius small r, and let me show you that if you look at this perpendicular right angle triangle here, this right angle triangle that you see, in this right angle triangle, everyone, be with me, you will understand this very easily. Okay, this is that right angle triangle that we are speaking about, in which this is capital R, this is theta, and this is small r. This is basically the ring that we are talking about. So you can understand that this ring has a radius r, and with respect to this right angle triangle, small r is going to be r sine theta. Okay, people? Okay, understood? And the thickness of the ring, this is the part which is the most complicated part to understand. Okay, the thickness of the ring, let me try to show you the thickness of the ring. Maybe you will be able to understand this in the first go itself. Okay, so everyone. So this is the thickness of the ring, which is obviously some small thickness that we want to talk about. And that thickness of the ring, if I subtend the angle from the ring here on the center, this is basically the small thickness of the ring. Okay, subtending very small angle d theta. Okay, so what will be this side? This will be capital R d theta. Means what is happening? Again, this is what is happening. That this is d theta. This is R, capital R obviously. So R d theta is the thickness of the ring. The rings which have been formed, their thickness is R d theta, capital R into d theta. So that is why you see this is R d theta which has been shown. That is the thickness of the ring. So now I want to write down the mass of the ring. Okay, let's just see how we are writing it. The mass of the ring is dm, and its area will be the circumference 2 pi small r into the thickness of the ring. That's how we wrote the area of any ring. Whenever we have to write the area of any ring, it is going to be the circumference multiplied by the thickness. Always remember this part very importantly. Again, for those who are finding this part to be confusing, either wait till the end of the class, because I've already explained this in center of mass explanation. I can give that explanation once again, but only at the end of the class. You'll have to wait for it, okay? Because that part is already done. So I will not spend more time here in explaining how the area of a ring is written as 2 pi r dr. So I'm writing it as of now 2 pi small r. Small r is the radius of the ring. Okay, I will write it in terms of capital R, don't worry. And the thickness of the ring is r d theta. As small r is variable, I'll have to write small r as r sine theta. Writing it, all of you. I have capital M pi, or rather 2 pi is going to cancel something here. So 2 pi cancels it 2 times, and see how things change. It becomes very easy. So I have m upon 2 r square equal to dm divided by r sine theta into r d theta. So from here, okay, see how beautiful this becomes. See this, guys. This is r square, this is r into r. Both are cancelled. See how easily we got the expression, or how simple expression we got of dm. It comes out to be m sine theta d theta divided by 2. This 2 is still there. It's not gone. This comes out to be the mass of the ring element, the biscuit. The biscuit packet is hollow sphere. How it is formed? It is formed by small biscuits. All biscuits are rings, different radius of the ring. Of any ring, as you know that all the rings don't have the same mass, so it depends upon the value of sine theta. If I speak about the topmost point where the ring of radius 0 is formed, its mass will also be 0. Put the value of theta as 0. So if you put the value of theta as 0, you get the value of the mass of the ring also as 0. You talk about the equator, angle becomes 90 degree. You put the value of angle as 90 degree, m by 2 d theta becomes the mass of that ring. Different values of theta gives you different ring mass. Okay. If you're understanding this, you will love the beauty of integration, how beautiful it makes things to be. And definitely, if you're not understanding it in the first go, you will have to watch it once again. And I request once again to all of you guys, if you have missed the center of mass explanation and the center of mass derivation of different objects where I explained the biscuit theory, I request you to once again go through that chapter today. It's only one session, center of mass, and then come back to this part today. So today is the second session where integration is exhaustively used. So pay attention. You definitely have to rewatch this first 1 hour of the session. Okay. So we have the dm value. What is dm? Dm is the mass of the ring. So what is the moment of inertia of the ring? We know that moment of inertia of the ring is dm into r square. But what is small r? We know small r is r sine theta. So it is r sine theta the square, and we will obviously be putting dm here. So I'm taking it to the next slide, and I will be integrating it from there. So moment of inertia I will be integration of dm into r square sine square theta. And what did we get as dm? Dm came out to be m by 2 sine theta d theta. So dm is m by 2 sine theta d theta, and this is r square sine square theta. So capital I m r square by 2. This is constant. Sine theta into sine square theta becomes sine cube theta into d theta. And this is where what I showed you guys here will be important. So definitely the derivation is lengthy. That's why I have taken few things already into account. Now what we'll be using will be the direct result of this integration from 0 to pi. Okay, 4 by 3 is what we'll be doing. 0 to pi. Now you understand how much time Suri sir has saved today, and a little bit of scary part is already done. So this part comes out to be 4 by 3. Okay, guys. Integration done on slide number 12. Slide number 12 where we have done the integration. So what do we get the moment of inertia finally? You see 2 cancels it 2 times. The final result is very simple, and it's something which you can always remember also. This is the moment of inertia of a hollow sphere. Not very difficult to remember, and obviously about an axis passing through the center and about one of the diameters. Moment of inertia, hollow sphere, 2 by 3 m r square. Okay, everyone, take your time, write it down. The final result is more important. If you want, you can draw a rough diagram also, a circle, axis of rotation passing through the center. Okay, guys. Okay, chalo guys. Now the next one will be very simple, but you'll have to remember the moment of inertia of a hollow sphere. It is 2 by 3 m r square. You have to remember this for the derivation of a solid sphere. So this is a solid sphere. Look at the difference now. Diagram may look exactly the same. The difference is now it has uniform mass density. Means what? It is basically the same difference which is there between a plastic hollow ball and a cork ball. Okay, or maybe a rubber ball, the full complete rubber ball or steel ball. Basically the mass is also present inside. Okay. How do I form a hollow? How do I form a solid sphere? The solid sphere is formed by having one hollow sphere at the center, very small, almost 0 radius, then a bigger hollow sphere, then a bigger hollow sphere, further bigger hollow sphere, more bigger hollow sphere, all of them being concentric, placed over each other one by one. So starting from the center of the solid sphere, or rather before the solid sphere was formed, you had a center, you had a hollow sphere, and then you have one by one more and more spheres being placed with increasing radius. That's how your solid sphere will be formed. Okay, guys, very important. It is uniform mass density. That means mass per unit volume is basically constant. Okay, so how do you write this for a hollow sphere? बिल्कुल वैसे लिखेंगे जैसे we used to write it for a ring. For a hollow sphere, it is going to be written as dm upon surface area into thickness. For a ring, we write it as circumference into thickness. For a sphere, hollow sphere, we will say it is circumference. Its circumference is basically its area 4 by r square into its thickness. That's how we are going to write it down. As this is again something that you should remember always. How do you write the density? The density means mass upon volume. Surface area, dimensionally area, thickness is dimensionally length. So it is volume that you have written in the bottom. Okay. So everybody, this is how I have chosen a random hollow sphere whose radius is small r. The mass is not small m. The mass is dm. Obviously, always the mass of the element that you choose is going to be dm. So people, see how we do this. The density will be written as the mass of the entire solid sphere divided by its volume, which is 4 by 3 pi r cube, will be equal to mass of the hollow sphere divided by its volume. And I showed you how do you write the volume, surface area multiplied by the thickness. So how much is the thickness? Thickness is dr, and circumference is 4 pi small r square into dr. Dimensionally volume, r cube, r square into dr is the r cube value. So 4 pi cancelled here. Okay, everyone. So just a second. Yeah, 4 pi cancelled with 4 pi, and dm comes out to be small r square goes there. 3 also comes in numerator from here. 3 capital M small r square dr divided by r cube. We have got this value. This is the mass of the hollow sphere. This is basically hollow sphere. This biscuit is hollow sphere. What is important is always to remember which object we choose as the elemental mass or the biscuit for different objects. I will give you a quick recap after this derivation. Don't worry. Okay, everyone. So what is the moment of inertia of a hollow sphere? I told you to remember this. It is 2 by 3 mr square, right? So here 2 by 3, yes, because I'm writing it for a hollow sphere now. The blue ring that you see is basically not a ring, but it is a hollow sphere. Okay, so 2 by 3 dm into r square. That's basically the moment of inertia of a hollow sphere. Yes, the interesting part. Now we are going to integrate 2 by 3 dm r square, and I'm going to put this. Just a second, right? Yeah, I'm going to put this dm over here. So see, you will have 2 by 3. Instead of dm, I will write it as 3 capital M r square dr divided by capital R cube multiplied by small r square. So you see 3 and 3 got cancelled. What I am left with is capital I equal to 2 by 2m by capital R cube. Okay, and integration of r to the power 4 dr. The smallest sphere is at the center whose radius is 0. The outermost sphere will have a radius capital R. That's the integration that we'll be doing. Let's do it on the next slide. So capital I for a solid sphere is 2 capital M by R cube. Integration of r to the power 4 dr 0 to capital R. So let's do the integration. Very easy it is. The integration comes out to be r to the power 5 by 5 from 0 to capital. I'll have to write it as small r to the power 5 by 5 from 0 to capital R. Okay, so this is r to the power 5 by 5. This will cancel it. R to the power 2. Final result, moment of inertia, is 2 by 5 mr square. That's our result. Okay, yes, important one, very important one in fact. This is what has happened so far. Okay guys, for a solid sphere, axis of rotation passing through one of the diameters. Okay, a quick recap. For a rod, I have not written it here, or the note does not say that. So rod, axis of rotation passing through the center like this, moment of inertia is ml square by 12. If we speak about a circular ring, mr square, circular disc, mr square by 2, solid sphere, 2 by 5 mr square, hollow sphere, 2 by 3 mr square, any diameter, the axis of rotation has been mentioned. That is very important. Okay. This is how it is. Okay, everybody. So you're going to use these values or expressions of moment of inertia so many times that you will naturally be able to remember them. But my piece of advice, write them on a piece of paper, stick it on your most favorite wall, and keep on looking at that expression again and again and again. You'll remember it. Okay, good. Now, a very simple point of moment of inertia for a rectangular plate. This is a rectangular plate. You can also consider it to be like, maybe this plate, which is rotated like this. If it is rotated like this, the moment of inertia is to be found. Its length about which the axis of rotation is perpendicular. Okay, this is the length, and axis of rotation is perpendicular to it. This is how the imaginary axis of rotation has to be seen. This is not the axis of rotation. Okay, this is not how the plate is rotating. This is how it is rotating. Remember that the axis of rotation is very important. So this is how the rotation is happening. Okay. Now the thing is, guys, be with me, and I will switch on the chat in some time. If I take this plate and somehow visualize this part, I will not be able to do this practically. If we compress it from the top and the bottom, okay, the mass will definitely remain unchanged. Capital M it is. Length of this portion will remain the same. Can I say it will become a rod of length L? Everybody, can I say that it will become a rod if I compress it like this from here and from here? If we compress it, or in the other way around, if it was a rod and I elongate the rod like this, it will become a plate without any distribution of mass changing. The mass is still distributed about the axis of rotation in the same way. Okay, so what is going to be the moment of inertia? Is going to be the same. This is going to be the biscuit. The biscuit has the same length as the object, but has the mass that is dm. So you will say that the moment of inertia di is 1 by 12 dm into L square, right? That's how you will write it. So the moment of inertia is going to be 1 by 12 into L square integration of dm. And what is integration of dm? It is the mass of the entire rod, sorry, entire plate. So it's going to be 1 by 12 ml square. It's the same result, which is of a rod. As long as the distribution remains unchanged, the result also comes out to be the same. Got it? Yes. This was our last derivation. Okay, but these 6 objects are very important for us to understand. Okay. Good enough. Let me show you guys, or rather, let's go to some problems quickly, and then I will give you a guru mantra. It's not my guru mantra, it's physics guru mantra, which will help us find out the moment of inertia of the same objects about different axes of rotation. Same objects, axis of rotation changed. You don't have to derive again and again. You will have certain theorems which will help you do the derivations very easily. Okay. Arey yaar. Because it is hollow sphere. Hollow sphere ka moment of inertia is 2 by 3 dm r square. 2 by 3 mr square. That's why. Okay. Okay, Prashank. Yes, actually, Ansh. Okay. Keep your questions noted. I'm still not opening for doubts yet. We have a lot many things to cover today. Chale aage. I will give you the formulas. Don't worry. I'll give you the formulas. Okay, Manav, don't worry. I'll give you the formulas as the question comes. I'm not testing you on formula. Don't worry. Okay, people. Yeah. Sure, guys. Question number 1 for all of you. Assuming that the density remains unchanged, we have a solid aluminium sphere of radius capital R, which has moment of inertia I about an axis passing through its center. Solid aluminium sphere. The moment of inertia about the same axis which is passing through the diameter if the radius becomes 2r. So the moment of inertia of a solid sphere is 2 by 5 m into r square. Whatever be the radius, you will put that radius value. Okay. So if you increase the radius, definitely the mass will also change. Density has to remain unchanged. No integration is needed in this question. Giving you already that idea. Okay. Giving you people 90 seconds. Find out the mass of the second sphere whose radius is 2r and then compare their moment of inertia. So if the moment of inertia earlier was I, now this is not L. In the options, it is capital I only. Okay, I'm just correcting the options. It looks like it is L that is written. They're looking for the moment of inertia only. Okay. Sure, people. Time starts in 3, 2, and 1. Last 30 seconds, everyone. Okay, everyone. Oh my god. Oh my god. What just happened here? So guys, if the density is same, earlier the mass was m, the volume was 4 by 3 pi r cube. If now the mass is to be found as m dash and the radius has become 2 r ka cube, then 4 by 3 pi gets cancelled. And what do I get? That it is m by r cube. This is m dash by 8 r cube, correct? 2 ka cube, r cube gets cancelled. So m dash comes out to be 8 times m, correct? Earlier the moment of inertia must have been 2 by 5 m r square. But now, pay attention. Now I dash will be 2 by 5 m dash into 2 r ka square. This is where most of you might have made a mistake by not considering the radius as doubled. Why? Because earlier the radius was r, mass was m, this was the axis of rotation. And now the radius has become double, the mass has become 8 times. So you'll have to accordingly write the moment of inertia. So I dash is 2 by 5, 8m into 4r square. 4 8s up, 32, 2 by 5 mr square. What is 2 by 5 mr square? It was the original value of moment of inertia. I dash comes out to be 32 times I. आया समझ में? You guys got your mistakes? Okay. Good, very nice. I didn't change the mass, then you are not paying attention to what I said. Okay. अगर density same रखनी है, volume बढ़ा दिया. Do you understand Hindi? So if the radius is increased, density is still the same. Don't you think that will be only possible when mass is also increased? So we have to find the mass. No. Yeah. For all of you, one more approach. If we find the moment of inertia as 2 by 5 mr square, what is mass? Mass is density into volume. So density is constant. So 4 by 3 pi r cube. Let's put it here. So the moment of inertia comes out to be 2 by 5 into rho into 4 by 3 pi r cube. This is the mass, and into r square. So everyone, this looks like 8 by 15 rho into pi. More importantly, r to the power 5. That's the more important part. That means I is proportional to r to the power 5. Now you don't have to worry whether mass will be increased or decreased or not if you're not able to think that. So I dash by I will be equal to 2r by r power 5. That is 32. कैसा लगा method? This is even faster than the previous one. I dash is 32 times I. But the condition has to be understood that density is constant. So because density is constant, that's why proportionality is seen with the radius only. Okay. Whichever works for you. Okay. So this one is the alternate method. Okay. Let's go to the next question then quickly. Good. Sure. Next question, everyone. This one is done. Next one is you have to find the moment of inertia of a thin uniform half disk of mass m radius r. It's half disk but has the same mass as the original disk and has the same radius r. Let me see how many of you guys are able to get this. I can only give you the hint that the moment of, or not hint actually, I can only give you the result of the entire disk. When the disk was complete, the moment of inertia was half mr square. That's all I can say. Okay. Now the disk has made half, but the half disk also has mass capital M. That's the important part to understand and remember and think about. Okay, people. It is half disk. It has the same axis of rotation. This is basically your disk side view. This is the axis of rotation. This is your disk. Okay, people. It is rotating about the same axis of rotation. It has same mass capital M and it has same radius r. So let's see how much will be the moment of inertia of the half disk of same mass, same radius. Giving you guys 45 seconds and the time starts in 3, 2, and 1. This is more of a conceptual question. Last 15 seconds now, everyone. Very good. The answer remains the same, half mr square. It remains the same. How will you visualize this? Think of a proper ring. Okay. Think of a proper disk. Think of a disk, but half of that disk has been folded like this. So this was the disk. Obviously, this is not right on the disk. I'm just giving you the feel of it. So maybe this is how the disk was in a plane. It was rotating like this. Now you have folded it from the center, and now you are rotating half of that disk. Moment of inertia still remains the same because the distribution of mass is still the same. I gave you the feel of it in the case of the ring. I told you the ring of half the shape, the ring of 1/4 of the shape. As long as the mass remains the same, distribution of the mass remains the same. Moment of inertia will come out to be the same. Okay. Even if you will fold it one more time to make it 1/4 of the disk, if you will fold it from here one more time. Okay. Imagine a chapati. Imagine a chapati at home which is being folded from the center to make a D. Imagine it one more fold, 1/4 of the chapati, but rotated about the same center, original disk. The moment of inertia will come out to be the same. Please give me a +1 if you understand this. There is more of concept than derivation in this question. If you understood the part how moment of inertia is dependent on the distribution of mass, you will never make a mistake in this. Never in future also. Remember, this point is a very important point, conceptual one. And this question is the one that you want to star mark. You want this question to revise every time before you go for an exam on moment of inertia or rotation motion. This is that level of question. Okay. Why would density increase? You are just folding it up. The same roti, if you fold it up, does it become double heavy? It still remains roti, it doesn't become double roti. Right? Yep, that's why. Cool. Sure, guys. Let's move on. We have that mass of the hard disk is the same. Now moving on. This is where the guru mantras come. We don't want to do the derivation again and again. The 6 derivations that we have done, they will be our standard derivation, standard results. Now we are going to talk about 2 theorems. One of them is called theorem of perpendicular axis. One of them is called theorem of parallel axis. First, we will study theorem of parallel axis. The other one will be the theorem of perpendicular axis. They help us find out the moment of inertia of the same object about different axes of rotations. Okay, same object but different axes of rotation. You will not again do the integrations. You will simply use the theorems. You will find out the moment of inertia. So what exactly theorem of parallel axis is? First of all, theorem of parallel axis is only valid for 1D or 2D objects. Okay, valid only for 1D and 2D objects. Okay, and I'm not getting into why, it doesn't matter too much. Okay, so here you have a two-dimensional object. A two-dimensional object could be a ring, could be a disc, could be a plate, could be that rectangular plate, and one of the axes is passing through the center of mass. This is a compulsory condition or necessary condition. One of the axes must pass through the center of mass, and the moment of inertia about that axis is ICOM and should be either known to you or is the one that you want to find out. Okay, so maybe ICOM is known to you, and now you are interested in finding the moment of inertia I about that axis, the dotted one, which is shifted parallel to the original axis of rotation. That means the two axes that you see in the diagram, they are parallel to each other, and the gap between them is r. Okay, so you have two axes, both of them are separated by distance r. More importantly, they are parallel to each other. One of them passing through the center of mass. That's why the theorem is called theorem of parallel axis. So what will be the result of moment of inertia about I is written here. It is written as ICOM, the moment of inertia about axis passing through the center of mass, plus mr square. What is r? R is the distance from r is the distance between the two axes of rotation. Okay, again, better that I give you an example of this. Okay, so have a look at this. We already have spoken about a rod whose mass is m, length is l. Okay, and the axis of rotation earlier was passing through the center of mass. This is your center of mass. ICOM or ICM is basically your moment of inertia that you already know. So what is ICOM? 1 by 12 ml square. You know this already. Now the axis of rotation, the new one that you want to find out, okay, is passing through one of the ends. Okay, it could be passing through any point, but right now the explanation is being done for a axis that is passing through one of the ends. So if the entire rod is of length L, the gap between them is L by 2. The gap between what? The gap between the two axes of rotation. So according to, okay, according to theorem of parallel axis, AXES is the plural for axis. Not getting into the technicalities of English here. So say this distance is d, L by 2 is d. So according to the theorem of parallel axis, I will be equal to ICOM plus mass of the rod into the distance between the two axes, square of that value, md square. So I'm writing it as d. You can write it as small r, up to you. Doesn't matter. It's not about what are you writing, r or d. What is important is the expression. So what is ICOM? You already know this, 1 by 12 ml square. Same mass, capital M, and d value is L by 2, square that value. Okay. So what do I have is ml square by 12 plus ml square by 4. Do the maths. You can multiply it by 3, divide by 3, or you can just simply take the LCM. You will get the final answer as 4 ml square, not final answer, semi-final answer. 4 ml square by 12. The final answer is 1 by 3 ml square. Another very important result, by the way. This is another very important result for us. The moment of inertia of the same rod passing through one of the end of the rod. That means what? Earlier, your rod was rotating like this. It was rotating about the center. Now it is rotating about one of the ends. This is how it is rotating. The axis of rotation is passing through one of the ends. That's why. So parallelly, the axis got shifted. Okay, that's one of the examples. 1 by 3 ml square is the result of it. Let's speak about a ring. Now we have a ring. Earlier, the axis of rotation was passing through the center and perpendicular to the plane. So this is ICOM. So this is a ring of mass m, radius r, and this is small d, and small d is equal to the radius. So the axis has shifted. Now the ring has axis of rotation that is passing through. It's passing through one of the. I should say it is passing through the tangent. It is tangent, but the tangent is perpendicular to the plane. Okay, the ring plane is this, and the axis of rotation is here. This is where the axis of rotation is. This is the kind of rotation that is happening. Okay, so everyone. So moment of inertia ICOM for a ring is mr square. Now I will be equal to ICOM plus md square, and d is equal to the radius of the ring only. So ICOM is mr square plus m into r square. The moment of inertia comes out to be 2mr square. Do I need to remember? No, please don't remember this result. The previous one is to be remembered. This one is to be remembered. This one is not to be. You can always do this derivation if required. Okay, easy once again. Two axes shifted parallel to each other by a distance d, which is capital R. Same thing we apply for a disc also. So now I have a disc. Radius, sorry, mass is m, radius is r, and maybe this was the axis of rotation earlier. This is ICOM. This is d, which is again equal to capital R. So ICOM was half mr square by 2. So I will be equal to ICOM plus md square. This is mr square by 2 plus m into r square. So mr square by 2 plus mr square. Do the maths. You will get the value as 3 by 2 mr square. Again, not to be memorized. These are not the results to be memorized. These are only explanation point of view. I'm giving you the examples of theorem of parallel axis. Okay, guys. I hope you guys are able to understand. The axis is only shifting by distance d. Could be any distance. The question will tell you how the axis is shifted, by how much distance it has shifted, and accordingly you will be solving this. Let me give you an example here. Oh, I'm not giving an example. This is a quiz. So again, a rod. ICOM is something that you know. ICOM is already mentioned in the question also. ml square by 12, and the axis of rotation is shifted by L by 4. So the new moment of inertia about this axis I is going to be how much is what you have to find out. I'll set up the quiz. You guys start solving. Okay. The theorem of parallel axis says I will be equal to ICOM plus md square. D you will have to figure out from the diagram. I'm giving you the diagram itself. And everybody setting up the quiz. Giving you guys 60 seconds. Time starts in 3, 2, and 1. ICOM is already given in the question, and you already know that also. Last 10 seconds, everyone. Okay, and the time is up. So decent number of people got this right, but could have been better. Could have been better, definitely. So ICOM is ml square by 12, and you can see the gap between these two is L by 4. Square that value. So ml square by 12 plus ml square by 16. So LCM is definitely 48. The answer is going to be 7 ml square by 48. Not doing the maths. You all can do the maths very easily about it. Take the LCM. After taking ml square common, you'll get this. Okay. Sure. One more. Now this is from JE 2020. This is from JE 2020 last year. You have 4 spheres, each of mass m, each of radius r. Okay, and they are placed on imaginary. They are placed on the corners of an imaginary square whose side length is a. Okay, the radius of the spheres is r. Definitely a is greater than r. Question says that if you have, one of the sides of the square as axis of rotation, then what will be the moment of inertia about this axis of rotation? So let me tell you guys, if I say this is sphere 1, sphere 2, sphere 3, and sphere 4, sphere 1 and 2, remember, listen to me very carefully, sphere 1 and 2 have the axis of rotation passing through their diameter. Okay, and for passing through diameter, ICOM, moment of inertia is 2 by 5 mr square for a solid sphere. Okay, but for sphere 3 and 4, the axis of rotation is parallelly shifted. This would have been their case also, but the parallel shifting of the axis of rotation is by a distance a. So you'll have to find out the moment of inertia of these two and then add all the 4 moment of inertias. The I net value will be I1 plus I2 plus I3 plus I4. Okay, I am going to set up the quiz for all of you. Start solving. I'm giving you 90 seconds and the time starts in 3, 2, and 1. I've already given you the value of I1 and I2, by the way. Or rather, the expression of I1 and I2 is given to you already. It's 40 seconds remaining, everyone. Last 10 seconds now. Okay. So let's see. Much better, everybody. So this should have been done very easily. We can say that I1 is equal to I2 is equal to 2 by 5 mr square because the axis of rotation for 1 and 2 is passing through their diameters. They are rotating the way Earth rotates about its own axis. But for 3 and 4, the axis of rotation is shifted by a distance a also. So I3 and I4 will be ICOM plus MA square. That means 2 by 5 mr square plus MA square. So now you'll be putting up all these values here. I net will be I1 and I2 both are same. So double the value. That will be 2 times 2 by 5 mr square plus 2 times I3 and I4 are also same. So that is 2 by 5 mr square. Okay, plus MA square. So when we simplify this part, everyone, we get the result as 4 by 5 plus 4 by 5, 8 by 5 mr square. mr square के terms को add करोगे तो 8 by 5 mr square it will come plus 2 MA square. Answer is option C. Okay, everyone. Good enough. So this was theorem of parallel axis. Now we'll learn one more theorem, which is called as theorem of perpendicular axis. This one is valid for any object, 1D, 2D, or 3D. Okay. The point is, in this one, you will talk about a body which will have, say, 3 axes of rotation as you see it in the diagram, X, Y, and Z, which are shown here. These are 3 axes, out of which X and Y that you see in the diagram, they are passing through the plane of the body. Means what? If I have to give the body as an example, if the axis of rotation is passing through the body like this, imaginary obviously, the body rotates like this, about X axis. Okay. If the axis of rotation passes through Y, again passing through the body, then the body rotates like this. So you see that this is how about X and this is how about Y. You have to visualize the axis. Z is the one which is perpendicular to the plane of the body, or perpendicular to the body and X and Y. The axis of rotation that is perpendicular to both of them. So then the body rotates like this. This is how the body rotates. Okay, that is IZ. So whenever such 3 axes are given, let's read what is written. The moment of inertia of a planar lamina about an axis perpendicular to the plane of the lamina is equal to the sum of the moment of inertia of the lamina, is basically the 2D object. I may be wrong. I might have said something which is not actually correct. Maybe it is valid. The theorem of perpendicular axis is valid for 2D and 1D objects. Okay, so I'll correct that. But as of now, so what is happening here? The 3 axes which are perpendicular to each other, the moment of inertia about the axis which is perpendicular to the plane of the body, IZ, is equal to IX plus IY. Okay, means what? The IX and IY are the moment of inertia about the axis which are passing through the plane of the body. That is compulsory. Okay, they need not be perpendicular to each other, by the way. Let me write that. X and Y, these are not coordinate axes X and Y. X, Y, and Z are not the coordinate axes. They are just 2 axes of rotation X and Y which are in the plane of the body. Okay, so X and Y may not be perpendicular to each other, but Z is perpendicular to both X and Y, and X and Y have to be in the plane of the body. Okay, also parallel axis theorem is applicable for any rigid body. I need to correct myself. Sorry about this. This is valid for any object. My bad. This is valid for any object. and this one valid only for 1D or 2D object. Most likely for 2D objects we'll be using. Okay, please don't ask me why, I don't actually remember also. Okay, but what is important is that you have to remember the final result. Iz is equal to Ix plus Iy. Okay, everyone, this is the result of theorem of perpendicular axis. X, Y, and Z axes are perpendicular to one another. X and Y are in the plane of the lamina, where Z is perpendicular to the lamina. They may have said X and Z are perpendicular to each other, but I have corrected it. X and Y may not be perpendicular to each other, but they have to be in the plane. Point O need not be the center of mass. Very important point. Point B is actually a very important point. Point O is not necessarily the center of mass. It can be any point. Okay. And third point, I've already corrected myself. Parallel axis theorem is valid for any object. Perpendicular axis theorem is valid for 2D objects and 1D also. Okay. I will again give you the examples of it. Say you have a ring. Okay. You have a ring of which Iz is something that you already know, and Ix and Iy you want to find out. That means what? Ix and Iy are the axes which are passing through the diameter, while Iz that you see is the one that you already know. It is passing through the center perpendicular to the plane. So Iz is mr square. That's something that you already know. So everyone, you can see that for the ring, because of the symmetry of it, Ix will be equal to Iy due to symmetry. The ring ka rotation will look similar about X and Y both. Okay, for any diameter axis, the ring will always look like rotating in the same manner. Okay, how is that rotation, by the way? I'll tell you what kind of rotation that is. It's basically taking the ring. This is the rotation. Yeah, this is the rotation. That rotation is basically Ix and Iy. Okay, so everybody, Iz will be equal to Ix plus Iy, and we want to find out Ix and Iy. So we are calling it 2 times of Ix or 2 times of Iy. Both are same because Ix is equal to Iy. So everybody, we can say Ix will be equal to Iy will be equal to half of Iz. And what is Iz? Mr square. So it is half mr square, the moment of inertia of the ring about a diameter. Very important for you to keep a note of it. How we found it? By using theorem of perpendicular axis. This is the theorem of perpendicular axis. Okay. Similarly, we'll go by a disk. So this time we have a disk, and for the disk, this is Iz, this is Ix, this is Iy. So the rotation that I showed you, instead of a ring, a disk is rotating like that. So I will say that Iz is known to us. It is half mr square. We did this derivation, by the way, today only. Okay. This was the derivation about z axis. We have already done it, half mr square. Now we want to find out Ix and Iy, which you see in the diagram. This diagram also it shows. So everyone will say once again, Ix will be equal to Iy again due to symmetry. So we can say, according to the theorem, Iz will be equal to Ix plus Iy. This is our theorem. This is equal to 2 times of Ix equal to 2 times of Iy. So everyone, Ix will be equal to Iy will be equal to half of Iz once again. So far everything looks same. It's only Iz which is different. So half of half mr square. So the result is going to be 1 by 4 mr square for a disk about one of the diameters, any of the diameters. Okay, guys, we get this. Okay, good. Now the interesting case. If you people remember, we spoke about this case. We got the result about an axis that is passing perpendicular to the length, or you can say this is passing through the planar lamina. The axis of rotation was passing through the planar lamina. So we know this axis of rotation. We know this axis of rotation, but we don't know this axis of rotation, the moment of inertia. That's what we find out. Iz we want to find out. Okay, and we are talking about a say we talk about a square lamina. We can speak about a rectangular lamina also. Okay, I will duplicate it. First, I will speak about a rectangular lamina. Means I am saying that this is B. This one is rectangular plate. This is a rectangular plate. And for rectangular plate, if I show you the axis of rotation for which you already know the moment of inertia, about this axis you know it is 1 by 12 ma square, and about this one it is 1 by 12 mb square. Whichever length you are perpendicular to, you tell the moment of inertia about that. So maybe this is Iy, maybe this is Ix, and this is Iz that you want to find out. Okay, very important. If I speak about Ix, X is perpendicular, or Ix is the axis of rotation that is perpendicular to A. This is what it is perpendicular to. So it will be 1 by 12 ma square. Similarly, Iy is about this axis which is perpendicular to B. So 1 by 12 mb square. Okay, with how you are compressing it. If you compress it perpendicular to perpendicular to A like this, then length becomes A. If you compress it like this, length becomes B of the rod, right? And now you want to find out Iz, which is equal to Ix plus Iy. So this comes out to be 1 by 12 ma square plus 1 by 12 mb square. That's 1 by 12 m A square plus B square. These are all important results. Perpendicular axis theorem results are important. The results that you are getting, and which axis that you are trying to find it about, you have to keep a note of it. Mental note of it is very important. Iz is the axis that is perpendicular to the plane. Okay, Z is perpendicular to plane of the plate. Okay, so for square plate, A becomes equal to B. Both are equal. So Iz, directly we will do this now. Iz, which is equal to 1 by 12 ma square plus B square. You will put A equal to B. 1 by 12 ma square plus A square. That means 2 ma square. So the result finally is 1 by 6 ma square. This is the result. Do you guys understand? समझ में आ रहा है? अच्छा, tell me one thing. If I elongate this plate, this is a square plate. If I elongate it, a 3D object it will become. What will it be? It will become a cube. For the square plate, if it is a square plate, if I elongate it, entire space is filled. It will become a cube. The moment of inertia will be still the same. 1 by 6 ma square. Okay, everyone. The feel of it is something that if you are getting it, you will be able to visualize it very easily. And for this, it will be cuboid. It will be cuboid here. Whatever be the height, does not matter. The moment of inertia will remain the same. Getting it? Okay, people. Chalo, quickly let's do a question. Yes, field is very important. That's why moment of inertia is one of the short topic of J. Try to find out the moment of inertia of the ring about tangent in plane of the body. if you know the moment of inertia about this axis, if you know this ICOM, remember this is ring, ICOM is the axis passing through the diameter. ICOM is not mr square. ICOM is not mr square. I'm clarifying this, or rather I'm helping you from making a mistake. I'm just stopping you from making that mistake. This is one very important thing that I'm telling you. We have just now found ICOM, and now the question is of not perpendicular axis theorem. The question is of parallel axis theorem. जो पहले सीखा था, उसका application है. Okay, giving you 30 seconds only, and your time. Parallel axis theorem you will apply, and the time starts in 3, 2, and 1. ICOM plus MD square वो लगाना है. ICOM plus MD square, because ICOM is something that you've already found. About one of the diameters you have already found. Okay, everyone. Let's see. Very good, guys. Very good. Okay. And no, the class is not over, obviously. So everybody, ICOM is basically about one of the diameters. It is actually a ring only. And for a ring, if the axis of rotation is one of the diameters, the moment of inertia is mr square by 2 now. So what is ICOM? This is actually an application of both the axis, theorem axis. So this is mr square by 2. This is by which the axes have been shifted. The parallel axes are shifted by d. So I will be equal to ICOM plus md square. So this is mr square by 2. And m, d ka value is capital R. So mr square, the answer is 3 by 2 mr square. That's your moment of inertia, the answer. Okay, everyone. Good. Now, the last topic of the day, called as the radius of gyration, also represented as capital K. Yes, kinetic energy is also represented as K. Radius of gyration is also represented as K. A very small topic. We'll be able to finish it up in next 5-10 minutes. Okay. So what exactly is radius of gyration? Let me first give you the idea of it, then I will show you the slide also. Say there is an object, a solid sphere, whose moment of inertia is known to us. Say that result comes out to be 2 by 5 mr square. If I compress this entire sphere, make it a point mass, and I have to make it move in a circle or circular path, the circle of, or I should say the point mass which is moving in the circle, to still have the same value, numerical value of the moment of inertia, the radius of the circular path for which you will get the same value of moment of inertia as that of this object is what we call as radius of gyration. I know 99% of the people might have understood anything that I've said, so I will repeat myself to give you a explanation once again. Okay, guys. So say, first thing, just focus on a circular motion. Just think of a circular motion. Okay, and in circular motion you have a point mass whose mass is m. Okay, moving in a circle about an axis of rotation. So you find out the value as moment of inertia as I. Okay, parallelly you think of any object given in a situation. It could be a sphere, it could be a hollow sphere, it could be a ring, it could be disk, it could be a rod, it could be a plate. And you calculate the moment of inertia of that object. Say you are talking about a solid sphere whose moment of inertia is given or is found as 2 by 5 mr square. You want this moment of inertia I1 and this moment of inertia I2 to be same. Okay, so you don't know the radius of the circular path. Let's say that radius has to be k value. For this k value, if I write the moment of inertia I1, okay, this is radius of gyration k. I1 value will be written as mk square. I2 is already written. For I1 to be equal to I2, the value of k when I try to find out is what we call as the radius of gyration for this solid sphere. So every object will have different radius of gyration depending upon which object and which axis of rotation you are talking about. Okay, everyone? I should have done this explanation in the later slides. Okay. Again, I will definitely show it to you first. So say you have any object whose moment of inertia is I, and you have a point mass of same mass value, but point mass. So for point mass, the moment of inertia will be written as mass into distance from axis of rotation the square, and that distance from axis of rotation is k. So the moment of inertia of the point mass is mk square. You equate it to the moment of inertia of that object, you get the value of the radius. That radius will be called as the radius of gyration of this object. Okay, like they have given you the example for finding the radius of gyration of a disk whose moment of inertia is half mr square. How do you get the radius of gyration? You get the value as r by root 2. That means what? If I have a disk which is rotating about its own axis, getting the moment of inertia half mr square. To have the same numerical value of moment of inertia, but for point mass, the point mass will have to go in a circle of radius r by root 2 to get the same numerical value of moment of inertia. Okay, everyone? Hope it is making sense. Let me give you an example for the same. Say the radius of gyration of a uniform rod of length L about an axis passing through one of its end and perpendicular to the length will be how much is being asked. Okay, so I have a rod for which the axis of rotation is passing through one of the ends, this one. Okay, so if the length of the rod is L, mass is m, you say that the moment of inertia of the rod for this value, for this arrangement, is 1 by 3 ml square. We did the derivation also. I told you this is important. The axis of rotation is passing through one of the ends. 1 by 3 ml square is the moment of inertia of the rod. This one. Okay, guys. So this one is being compared to a circular motion. Now I compare circular motion of a point mass having the same value of mass. So what should be the radius in which it should rotate to give the same value of moment of inertia? Okay. So let's call this moment of inertia to be I. That value should be equal to mk square. Now equate these two. Mk square to be equal to 1 by 3 ml square. M will get cancelled. The radius of gyration comes out to be L by root 3. I hope you guys are able to do this maths by yourself. Taking the square root, it comes out to be L by root 3. Okay, that's our answer here. The moment of inertia of the rod and the point mass when equated, the radius of the circular path has to be equal to L by root 3. That's the answer. Okay, guys. We'll give you one more example. So here, the radius of gyration of a uniform rod of length L, again a rod, but passing through the center of mass. The axis of rotation is passing through the center of mass. Okay, just hold on, guys. Don't be in a rush. This is I that we want to find out. Mass is m, length is L. You know that in this case, the moment of inertia of the rod is 1 by 12 ml square. Compare it with mk square. Always you will compare it with mk square only. Radius of gyration is defined for a circular path only. K will be the radius of gyration. M cancelled. K comes out to be L by root 12, and root 12 is basically 2 root 3. So L by 2 root 3. Oh, they have given the value as L by root 12 only. This is dimensionally incorrect. L square by root 12 is not possible. So we got the value L by root 12. Okay. Let's spare 2-3 minutes more, do these questions so that we don't leave anything for the next session from this particular slide. So now the numerical part. Numerically, you will have to compare this. The radius of gyration of a body is given, the moment of inertia of a body is given, mass is given, you have to just find out the radius of gyration. So question wants you to find out the value of K. You have to just find out the value of K. I is given, M is given. Whatever that body is, its radius of gyration is to be found, giving you 45 seconds. Time starts in 3, 2, and 1. Find the value of K, everyone. Just one more question after this, okay? And we'll be done. And this is definitely a very important session today. So I cannot leave it hanging. That's why I'm completing the entire field of the chapter. So that when you watch the replay, you get the entire understanding of moment of inertia along with the radius of gyration and the theorem of perpendicular and parallel axis. Last 10 seconds, everyone. In options, M represents meters, not mass, okay? Because it's a numerical question. Very good, yeah, very good. Awesome, well done. Good. So K will be equal to I by M in under root. So that is 20 by 4. That means root 5 meters. Okay. The last question, and this one is from 2018. It's actually not from radius of gyration, it is a general question. Okay, so I'll give you this question as homework. You will have to figure out what's to be used, and this is going to be a homework question. We will do this problem next time. This is not from radius of gyration. Okay, the correct answer is also given as option A. You try this, and we'll discuss it next time. Okay, people. Good. So this is the formal end of the class. Let me show you the leaderboard. Okay, everyone. Congratulations to those who made it to the leaderboard today. This was more of a theory session, less number of numericals done this time. Going forward, you will have relatively lesser theory, at least in the next session, and then more problems will be found. Okay, start solving moment of inertia questions from Tattva also, very important. Okay, all of you, congratulations once again, taking the leaderboard off in 5, 4, 3, 2, 1, and taking it off. Okay, and as you will any which way demand for it, giving you that spaceman, astronaut. Great job, everyone. You need to definitely watch the replay of this session. Means this one will require you to go through the replay once again for better understanding. Okay. 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 So this brings us to the end of the session. Those who want to now exit the session can exit. Class teachers, once your doubts are done, you can also exit the session. Okay. Tushit, your microphone is not working. Okay. Yes, Irfan. The radius of gyration question. This one. Because axis of rotation is passing through the diameter. This is the axis of rotation, Ix and Iy. The axis of rotation is not Iz. Same object about different axes of rotation has different moment of inertia. That's why moment of inertia is a tensor quantity. Okay. Okay. Yes, definitely you need to watch the replay. Good for you, Manan. Yes, Akul. Yes, Akul. Derivation. Okay. Solid sphere or hollow sphere? Solid sphere. This one. Tell me. Definitely, but वो लेंदी होगा इसलिए नहीं करना dx उसमें एंगल वाला इंटीग्रेशन नहीं होगा ऐसा उसमें एंगल वाला इंटीग्रेशन नहीं होगा उसमें तुम्हें मानना पड़ेगा कि उसकी हाइट y है और y का वैल्यू जो है +r से -r तक जाता है या -r से +r तक जाता है नीचे से ऊपर जाता है तो y का वैल्यू फ्रॉम द सेंटर व्हेन आई विल मेजर साउथ पोल इज -r डिस्टेंस नॉर्थ पोल इज +r डिस्टेंस एंड थिकनेस विल बी dy लाइक दैट डन बट प्लीज गो विद द होलो स्फीयर वाला अप्रोच बहुत इजी होता है वो इसलिए ठीक है ओके ये समझ बोल ये जो रिंग है अलग अलग रिंग्स जब मैं फॉर्म करूंगा ताकि मैं पूरा होलो स्फीयर बना सकूं ऐसे तो जितनी भी रिंग मैंने बनाई उन सबके रेडियस सेम नहीं है सबसे ऊपर जो रिंग बनेगी उसका रेडियस 0 सबसे नीचे जो रिंग बनेगी उसका रेडियस 0 जो इक्वेटर पे बनेगी उसका रेडियस कैपिटल R ठीक है तो अगर इन सबकी लोकेशंस को मैं एक ऐसे लाइन से डिनोट करता हूं जो नॉर्थ पोल से साउथ पोल तक जाने वाली है मतलब जब रिंग सबसे ऊपर है ये जो पेन है ये सेंटर ऑफ द स्फीयर से जुड़ा हुआ है O से और इसका जो टिप है ये वाला पॉइंट वो स्फीयर के रेडियस के बराबर है ये बात समझ में आ रही है ये है वो पेन जो मैंने रेड वाला वेक्टर बनाया ना ये वो पेन तो अब सोचो सबसे ऊपर जब रिंग होगी तो ये पेन भी वर्टिकल होगा जो रिंग सबसे ऊपर होगी उसको ये पेन भी बिल्कुल टच करूंगा तो एकदम वर्टिकल पोजीशन दिखाएगा बेसिकली मैं पेन को ऐसा दिखाऊंगा ये होगा पेन है ना ग्रीन वाला और जब सबसे नीचे होगा तो ये भी वर्टिकल डाउनवर्ड आ जाएगा तो ये कितना एंगल घूमा 0 to 180 एग्जैक्टली तो इसलिए एंगल का वैल्यू 0 से 180 जा रहा है रेक्टेंगुलर प्लेट मतलब परपेंडिकुलर एक्सिस थ्योरम या पहला डेरिवेटिव हां ये वाला हां हाँ, तुमने एक्चुअली रॉड को एलोंगेट कर दिया या बड़ा कर दिया, ऐसा सोचो। वो जो बीच में रॉड है या ग्रीन वाली, अगर उसको मैं ऐसे खींच दूं तो प्लेट बन जाएगी ना। मास अभी भी जितना एक्सल ऑफ रोटेशन से राइट में, उतना एक्सल ऑफ रोटेशन से लेफ्ट में m/2 डिस्ट्रीब्यूशन ऑफ मास अबाउट एक्सल ऑफ रोटेशन स्टिल द सेम। इसलिए मोमेंट ऑफ इनर्शिया भी वही आया 1/2 है ना। थैंक यू, थैंक यू, थैंक यू। ओके बाय, थैंक्स। चलो तुषित से बात करेंगे अब। तुषित का माइक्रोफोन काम नहीं कर रहा था पहले। यस तुषित, गुड मॉर्निंग में चले गया, जब जागो तब मेरा बोलो। यूनिफॉर्म सॉलिड स्फीयर का डेरिवेशन क्या? एक मिनट, ये रहा सॉलिड स्फीयर। हाँ बोलो, बोलो ना। हाँ भाई, अभी वो यही तो, जो भी पहला स्टूडेंट जिसको अनम्यूट किया था उसने भी यही बोला था, तो मैंने बताया भी कि तुम वो भी कर सकते हो कि यहाँ एक डिस्क कंसिडर कर लो, उस डिस्क को कंसिडर करो वाई हाइट के ऊपर, और इसका विड्थ कंसिडर करो डी वाई। ठीक है, तो ये आर हो गया, ये वाई हो गया, और ये उसकी रेडियस स्मॉल आर हो गई। तो मतलब एक ऐसा ये बनेगा रेक्टेंगल, सॉरी एक ट्राइंगल बनेगा जिसमें ये स्मॉल आर है, ये वाई है, ये कैपिटल आर है, समझ गए। तो इसमें आर का वैल्यू चेंज होगा, वाई का वैल्यू भी चेंज होगा, और विड्थ डी वाई है। तो तुम क्या लिखोगे, इसका डीएम मास लिखना चाहोगे। डीएम मास कैसे लिखोगे, डीएम मास होगा इसका एरिया मल्टीप्लाइड बाय द थिकनेस। सिलेंडर है ना, ये जो डिस्क है वो एक्चुअली सिलेंडर ही है। थीटा मत लो कभी भी, यही स्टैंडर्ड अप्रोच है। मैं एक्सप्लेनेशन नहीं दूंगा बहुत ज्यादा, क्योंकि बहुत इंटीग्रेशन वाला एक्सप्लेनेशन है जो अभी हमें समझेगा नहीं, क्योंकि मैथ्स में हमने इंटीग्रेशन पढ़ा नहीं है। तो इसलिए मैंने बोला कि जो हॉलो स्फीयर है उसमें थीटा वाला अप्रोच चलता है, और जो सॉलिड स्फीयर होता है उसमें डिस्क वाला अप्रोच चलता है, जिसमें हम लोग थीटा की लोकेशन नहीं चेंज करेंगे, या अगर थीटा से लोकेशन नहीं बताएंगे, हम वाई से लोकेशन बताते हैं, और वाई का वैल्यू चेंज होगा माइनस आर से लेकर प्लस आर तक के लिए। ठीक है, और मैं तो पर्सनली इसको भी अवॉइड करता हूं, मैं हॉलो स्फीयर कंसीडर करता हूं एज डिस्क्स। वो बहुत ईजी हो जाता है एक्चुअली। इसमें गड़बड़ हो जाएगी, इसमें गड़बड़ हो जाएगी एक्चुअली, इसमें गड़बड़ हो जाएगी, तो इसलिए करना भी है तो भी मैंने आपको बताया वैसे करना। ठीक है, ओके। अंश, थोड़ी देर रुकना पड़ेगा बेटा, तुम सेंटर ऑफ मास वाला डाउट पूछे इसलिए। सर आपने कहा था कि मैंने, हाँ मैंने कहा था, मैंने भी कहा था टाइम बचेगा, तो टाइम नहीं बचा बल्कि टाइम कम पड़ गया हमें। व्हाई डोंट यू कंसीडर इन द सेम आलेख, एक्चुअली इस बात पे डिपेंड करेगा कि ऑब्जेक्ट जो है आलेख, वो इस बात पे डिपेंड करेगा कि ऑब्जेक्ट सिमेट्रिक है भी या नहीं। अब रिंग या डिस्क है तो सिमेट्रिक है, लेकिन अगर रेक्टेंगुलर प्लेट है तो सिमेट्रिक नहीं है। तो वो इस बात पे डिपेंड करेगा कि ऑब्जेक्ट क्या है। डिस्क और रिंग में तो कोई तकलीफ नहीं है, बहुत ही बढ़िया, लेकिन अगर मान लो वो एक रेक्टेंगुलर प्लेट हो गई तो प्रॉब्लम हो जाएगी। तो उसमें हमें अलग अलग मानना पड़ेगा एक्स और वाई को। इनफैक्ट स्क्वायर प्लेट होगी तो भी शायद प्रॉब्लम ना हो, अगेन आई थिंक शायद प्रॉब्लम ना हो, क्योंकि अगर वो एक्सेस ये दोनों है तो कोई प्रॉब्लम नहीं, लेकिन अगर मान लो एक एक्सेस जो मैंने बनाई हुई है वो है, दिख रहा है डायग्राम, दूसरी एक्सेस अगर ये बना दी तो, जो कि इसके डायग्राम के पास हुई है, तो है तो दोनों सी प्लेन में, लेकिन दोनों सिमेट्रिक नहीं है एक दूसरे से। तो आई एक्स और आई वाई डिफरेंट हो गया अभी। ठीक है, इसलिए नॉट नेसेसरीली आई एक्स एंड आई वाई विल ऑलवेज बी सेम। ठीक, ओके। Is the name of this batch Drishti C JE Elite? No, it's not Drishti JE C Elite batch. This is Drishti CE JE batch. That's it. Thank you, Siddharth. Bye 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 bye. हो गए सबके डाउट्स हो गए? अरे विहान के डाउट्स नहीं मिलते हैं। ये बोलो। थैंक यू, थैंक यू। क्या बोल रहे हो? अच्छा, सुनाओ। मतलब बुढ़ापे वाली पूरी देख के रहोगे आज? ठीक है, ठीक है, सुनाओ सुनाओ। Lovely, lovely. Thank you so much. And let me tell you, this is for the first time somebody has written and said a poem for me. But this was lovely. This was really good. Thank you so much. Thank you so much. I'm actually glad to have all the students of Vedantu with me, and I'm glad that all of you guys are there and still able to bear with me my short temperedness at times. I know I'm very short tempered. Everybody knows this around me, and I know my 11th standard batches don't get that feeling. 12th standard batches don't get that feeling. जो लोग मुझसे शुरू से पढ़ते हैं ना, उन्हें मेरा नेचर समझ में आता है, पर जो लोग मेरे से बीच में जुड़ते हैं उनको गुस्सा आता है मेरे पे. They actually hate me. थैंक यू तनिष, थैंक यू. अभी बोलो, कुछ डाउट भी है क्या? कुछ नहीं है, आया समझ में सब कुछ. That's good. Absolutely. ये वाला तो पूरा देखना पड़ेगा तुम्हें. ठीक है. Cool. ठीक है, चलो फिर. Have a good day. Thank you, thank you. Bye bye. Bye bye. Good night. Harshita, again, I'm really sorry that I'm not in the right position to help you with that. All I can tell you is you need to speak to your SAM and raise this concern. This is again an operational problem or a subscription-based question, so you will have to speak to your SAM. Okay? Yes, Monish, definitely I will unmute you. Yes, good evening, good night, good morning, everything is fine. Tell me. This one. Those are point masses. These are spheres. These are spheres. They have different radius. They are not point masses. That's why. If they become point mass, if this question says now they're point mass, you can put the value of r as 0. You will get the answer same as the previous one. The answer in the previous session question was 2ma square. So that is the answer that you will get if you put r value as 0. That's the difference. Okay. Bye-bye. Thank you. Thank you. Sir, when are you going to Bangalore? Even I don't know. Wait a second. Ansh, wait. I'll call you personally. Don't worry. Bye fun. Sir, मेरा question, Ansh का question. Okay, why Bangalore? Because Bangalore is the headquarter of Vedantu. Okay, Ansh ने बोला a thin bar of length L has a mass per unit length lambda that increases linearly with distance and total mass. Blah blah blah. Center of mass पता नहीं, ठीक है. So Ansh, let me unmute you. Ansh, your microphone is not working, so no problem. So Ansh, hope you remember the derivation of the center of mass of the rod, the uniform rod. Remember that? Remember that, right? Now I'll just give you the idea how it will be done. Then you'll be able to do it by yourself also. So what we did, we said that at a distance x, consider a small elemental mass dm whose length is dx. Yeah. Remember? Yeah. So there we used to say the entire mass of the rod and divided by the length of the rod is equal to dm by dx. This was valid there. Remember? This was valid there. But it's no more valid here. It's not valid here. Why it is not valid here? Why? Because lambda is not constant. Because lambda is not constant according to your question. Okay. So according to your question, lambda is some k times x, where k is a constant. So k is a constant. So you will say now lambda will be dm by dx only. Now dm by dx will be equated to lambda, which is equal to kx. Okay. ये बात समझ में आई? Because lambda is proportional to x. That simply says as you move more and more and more to the right, the rod becomes more and more heavy. There is less mass on the left part, more mass on the right part. That's why the density is more on the right portion. So from here, you will say dm will be equal to kx dx. What the value of dm? Now you will simply find out the location of center of mass by saying center of mass location will be integration of x dm by integration of dm. Okay. This time you will not say the denominator is capital M. You will not say that. You will have to integrate it from 0 to L for both. You put the value of dm here and you put the expression of dm here and integrate from 0 to L, you'll get the answer. ये k जो है वो cancel हो जाएगा from numerator and denominator both. K does not increase. K is constant. Lambda increases. K is the proportionality constant. Understood? So do this derivation from here, you will be able to get the answer also. अच्छा लैम्डा नॉट दिया है तो k की जगह पे लैम्डा नॉट दिया है क्वेश्चन ने तुम्हें ऑलरेडी लैम्डा नॉट दिया है तो k मत लिखो लैम्डा नॉट लिख दो ऐसे बस आंसर ऐसा हो जाएगा ये दिया ना क्वेश्चन में लैम्डा इज इक्वल टू लैम्डा नॉट x ओके हाँ इंक्रीजेस लीनियरली का मतलब वही है लैम्डा इज प्रोपोर्शनल टू x तो लीनियर इक्वेशन बन गई यस अशरा ओके अंश there you go Paridhi, you can actually see these points in the PDF also. Okay, thank you Ashita, thank you. ठीक है everyone, should we call it a day now? Okay, shallow then guys, bye bye, hasta la vista. Yes, good night everyone. Okay, yes Paridhi, I said I corrected those points. I corrected it. They need not be perpendicular. I have corrected this point. Okay, you can actually skip this point. Let me remove this point. Okay, x and y need not be perpendicular to each other. Okay, परसों मिलेंगे ठीक है चलो गाइस बाय बाय गुड नाइट साइनिंग ऑफ ओके विशेष ओके थैंक यू बाय बाय गाइस साइनिंग ऑफ नाउ सी यू ऑल ऑन